Magnetic fields can have many different interactions with particles. It can have specific interactions with a wire that's conducting electricity, which we can quantify in essence with equations. So if we, for example, I'm going to describe an observation that you can observe in the laboratory, in your physics lab. Just get two magnets. So you have a north magnet, get another magnet, a south magnet, okay? South magnet. Then have a wire just running in that direction, okay? And have a current pass through it in this direction. What you'll find is, in this case, because of the way that this is arranged, you'll find that the wire is, as soon as you activate the current, or as soon as you let the current pass through the wire, you'll find that the wire is deflected downwards. And the reason why this occurs is actually, well, first of all, let me talk about the thing that you need to, the sort of equation or sort of technique that you need to know. Let's quickly look at what's involved here. So I'm going to use another color, perhaps yellow maybe. So we know that the magnetic field is in this direction. So uniform magnetic field acting down here. This uniform magnetic field acts from north to south. Of course, it's not uniform. There are, curvy bits over here, but we'll not worry about that. A uniform magnetic field is present. The current is acting perpendicular to the north-south plane, right? And what I'm going to do now is show you a cross-sectional view of this. So if we have, let me go back to green. If we have our south magnet over here, and we have our north magnet over here, we have field lines going through here, magnetic field lines, of course, but also we have this wire passing through, which also has a magnetic field, and because it's coming out the page, the right hand rule suggests that it will act in this direction. In this direction, right? In this direction. But we won't draw the outer ones, we'll just draw the inner one, okay? Because it's coming out the page, the magnetic field, according to the right hand rule, so if you wrap your fingers around the, god damn it man, what the hell is this? If you wrap your fingers around a wire in a clockwise fashion, and you point your thumb up, if you raise your thumb, you'll see that your thumb points in the direction of wait, let me restate that. Sorry. If you have a current carrying wire, point your thumb in the direction of the current, and then wrap your fingers around the wire, and the direction which your fingers wrap around is the direction of the magnetic field. Okay. Right. Now, back to this. What we have here are magnetic fields from the magnets, and we also have a magnetic field from the wire. In essence, because of the way that this is arranged, what you'll then get is an addition, a vector addition of the different magnetic fields. So you'll get something sort of like this occurring, right? Something like this. You'll have some sort of something like that, a little bit like that. Kind of like it looks kind of like a catapult. Oh, sorry, my bad. I did it wrong. It would be something like, if you have the wire here, it would be something like this instead. And then it will be kind of concentrated over there, and there'll be a lot of flux over here, which is actually causing the movement downwards of the wire. It's the vector addition of the different magnetic fields. So in essence, that's why this goes downwards. A good way of kind of understanding this is Fleming's left-hand rule. So Fleming, if you take your left hand, right, you'll have I'm trying to draw a hand. So you have your thumb, okay? Have your thumb. You have your first finger, and you have your second finger, okay? And you have your other fingers over here, which are not required. So your first finger points in the direction of the magnetic field. magnetic field. Your second finger points in the direction of the current, conventional current, and your fifth finger shows the direction of the force that's applied, or the direction of the force that's applied to the wire. Okay, and that's known as Fleming's left-hand rule. Okay, Fleming's left-hand rule. Now, this is the interaction between a current-carrying wire and the a uniform magnetic field, and you see that the current causes a force or induces a force upon itself. You can also get something else occurring, or you can have induction of a current, which we'll come across in a second when we're dealing with transformers, but I might as well mention it now. If you have, again, you'll have a uniform magnetic field, north to south, okay? Two different magnets. But instead, this time you're just going to have a normal wire, okay? A normal wire with no current in it. No current, okay? And you still have your uniform magnetic field that passes from north to south. North to south, the uniform magnetic field still stays there. But now, instead of there being a current, what we're going to do is we're going to move the wire upwards. Physically, we're going to move it upwards. Now, what you'll see is if you connect this to an ammeter, for example, and this connection also to the ammeter, you'll find that you'll get a current flowing, and the direction of the current is determined based on another rule. This time it's the right-hand rule. So you have your thumb, you have your first finger, and you have your second finger. Same things. Your thumb represents the force or the direction in which we move the wire. This represents the magnetic field again, the first finger. And this represents the current. And this is known as Fleming's right-hand rule, the induced current, let's say. And this is known as Fleming's right-hand rule. So in this case, because the force that we're applying is upwards, and because the current, at least the magnetic field, is pointing downwards, the current will actually move in a backward direction, that direction. And also the induced magnetic field will oppose the original magnetic field, which we're not going to discuss at the moment. But based on Fleming's right-hand rule, you can then see that the current that's induced is in the opposite direction to this thing over here. And induction is something that's very important for A2 physics, which we'll be discussing in future topics, but for now, that's pretty much all you need to know. Now, in that situation, we saw that the wire was being deflected by a particular force, right? Let's say that the force is acting upwards. Is there any way in which we can determine that force in terms of newtons? And it turns out there is. There's actually an equation that you can use. The equation is F is equal to BIL. Okay? F is equal to BIL. F is the force in newtons due to the magnetic field. B is the magnetic field strength in Tesla. I, of course, is the current in amperes. And L is the length of the wire in meters. Okay? And this, of course, is in newtons. And that is the defining equation of how a wire interacts with a magnetic field and the force that's induced upon it, let's say. To be honest, this equation is actually derived from another equation. I'm going to quickly show you how this works. The other equation, the more fundamental equation, is F is equal to BVQ, and that's in terms of a moving particle. Let's say it's an electron. An electron that's moving at a velocity of v. Okay, this is based, of course, on the current. The wire, for example, it's moving at a velocity v, and it's got a charge, of course, of 1.6 times 10 to the minus 19. F equals BVQ. However, we know that velocity is equal to distance or length over time, let's say. Length over time, and charge, of course, is equal to what's charge equal to? Charge is equal to coulombs, right? Of course, then what we know is that coulombs per second is current. So in essence, what we can then do is derive F equals Bill. But I'll go more into the other equation BVQ in another video. But for now, I'll just show you guys how it's derived. So the equation that you need to know for this particular chapter is this one, and I want you to commit it to memory. F is equal to Bill. It's pretty easy to remember because it's got Bill, right? I mean, it's kind of like a name. F is equal to Bill. Once you memorize this equation, everything that's associated with this particular topic will be pretty much second nature to you. We can use this idea to explain certain things. You probably have come across this already, but I'll show it to you guys again in case you haven't. A simple motor is based on the principle that a force is experienced by current carrying wires. So in the case where we have a coil, I'll just represent a very simple motor. Okay, we have a motor which has two different or a split ring that occurs here to alternate the current direction. Okay, so you have a single wire that's coiled into this shape. Let's say that the current, this of course is connected to a circuit. Okay, conventional current flows from positive to negative, so the current of course flows that way and comes back that way. Okay, and based on the knowledge that we've gained from this video, we know that using Fleming's left-hand rule, we know that this side will go downwards and this side will go upwards. There will be a force that's induced. Of course, once there's a 180 degree rotation, thanks to the split ring commutator, you can find diagrams online. I'm not that good at drawing, but what the split ring commutator will do is then alternate the current that's going through this side of the coil, so that it acts in that direction and is moved downwards. And in essence, what that allows is the coil to spin in this anti-clockwise direction. And that's basically the principle of a simple motor. And that's something that I want you guys to take from this lesson. Basic idea is that a force is exerted on a current carrying wire. You can induce current in a wire based on movements through a magnetic field, and the movement has to be perpendicular. Well, it doesn't have to be okay, so wait a minute, let me show you. A current carrying wire will experience a force if it's perpendicular to the field. In this case, the wire is moving perpendicular to the field, right? So it will experience a force. Technically, this is not true. It's actually just the component that's in perpendicular. So you could have a wire, for example, acting in this direction, and it would still experience a force, but the force would be lowered because there'd be less of it acting perpendicular. This equation that I wrote up here, F is equal to Bill, that's technically F is equal to Bill sine theta. F is equal to Bill sine theta because of the fact that based on whether the value of theta is big or not, you can determine if the force that's going to be exerted is going to be perpendicular or not. But that's something that you don't need to worry about for now, hopefully, in your course. So yeah, just take that away from this lesson, review the lesson, make sure you understand these principles, because the next part of the series will be focusing on some more complicated ideas, which will require a basic understanding of the topics that we covered in this video. So I'll catch you guys later. Bye bye.